All right, we're moving on to colligative properties. So let's go ahead and define what those are. So colligative properties are solution properties that depend upon how much solute is present. All right, so this is a quantity association with solution properties. So how much solute you put in there, right, you're going to affect the solution properties. But what's important about this is this does not depend on nature of solute. All right, so you could add glucose, glycerin, nitrobenzene. If you add any of those things, you're going to change the solution properties, but it only will change based on how much of each one of those you put in. All right, so that's quite a bit different than something like, let's say, a solution property pH, right? So if you add acid, all right, that's a nature of a solute, you're going to affect the pH. All right, so pH would not be considered a colligative property. So we classically discuss 4 of these colligative properties, and we're going to go through them in turn. The first one is called vapor pressure lowering. The next one we're going to look at is really a consequence of vapor pressure lowering, but it is boiling point elevation. The next one is going in the other direction. We're going to look at freezing point depression. And finally, osmotic pressure. All right, so a lot of these, well, the first 3 colligative properties we're going to look at are temperature dependent. All right, so what we need to do is look at units of concentration for solutions that are not temperature dependent. So back when you discussed solution chemistry and stoichiometry in first semester topics, a very handy unit of concentration is molarity. All right, so molarity is given by the capital M, all right, symbol capital M, and it is defined as mole solute divided by the liters of solution. All right, that is a very handy unit of concentration. However, it's temperature dependent, right? Because right here you have a volume of a solution, and volumes are affected by temperature. So we need to find some units that are not temperature dependent, and 2 that we're going to use in colligative properties is something that sounds like molarity, unfortunately. It's called molality, right? And it gets the symbol of a lowercase m. So it's quite difficult to tell the difference sometimes between an uppercase and a lowercase m, so I try to dramatically put that little tail on my m to indicate that I'm dealing with molal, all right? So molality is defined as mole solute, again, on top, but the bottom is going to be different. We're going to talk about the kilograms of solvent, all right? So something quite a bit different here. We're dealing with a mass term, kg, which is not temperature dependent, and rather than the solution, we are only looking at the solvent, all right? So it's kg solvent, whereas molarity has liters of solution. All right, and another handy unit is something called mole fraction. So we use the Greek symbol chi, which is an x, essentially. So it's a x chi. And then we say chi A, all right? So this would be the mole fraction of A is how that is translated. So the mole fraction of A is defined as the mole of A divided by all other moles in solution. All right, so another way to look at the mole fraction, chi A, let's say you have a solution, and we're going to put A in red, and then component B in blue. All right, so if I wanted to look at chi A, that's going to be the mole of A divided by the mole of A plus the mole of B. All right. You can also express mole fraction in component B, where you could say chi B would be the mole of B divided by the mole of B plus the mole of A. And you can imagine if you had a third component, all right, you would have to put mole of C in the denominator, and if you had a fourth component, you need to put the mole of D in the denominator, or what's on the bottom. All right, so that's how we define mole fraction, and we'll use these as we're going forward. All right, so let's do an example of using these two. Let's say we have I can ask, what are the mole fraction and molality of a solution that contains 0.850 grams ammonia NH3 in 125 grams of water, H2O. And we're going to take these one at a time. All right, so if we're going to look at the mole fraction, so if we're going to look at the mole fraction of ammonia, so chi NH3, that's going to be the mole of ammonia over the mole of ammonia plus mole of water. So now what we're going to need to do is convert our masses of ammonia and water into mole. All right, so the mole of NH3, we have 0.850 grams NH3. And to convert grams to moles, we need the formula weight of ammonia. And the formula weight of ammonia is 17, and that comes from one nitrogen atom having a molar mass of 14, and then we have the 3 hydrogens, so that gives us 17 grams per 1 mole. All right, so our grams cancel, and I get 0.05 mole. All right, for my ammonia. For water, I get, what did we have? We had 125 grams of water, and the formula weight of water is 18 grams per 1 mole. And that comes out to 6.94 mole. All right. So we have our moles of ammonia, 0.05, and our moles of water. All right, so now what we need to do is put these together in our mole fraction equation. So chi NH3 again is going to be equal to 0.05 mole divided by 0.05 mole plus 6.94 mole. And when I compute that, I get a value of 0.00715. All right, and of course this mole fraction is unitless because it's mole over mole. All right. Now, the next exercise that we had to do was calculate the molality of NH3. So So this will be a little easier because we've done most of this work. That is what? The mole of ammonia over the kg of solvent. So the mole of ammonia we've already done is 0.05 mole. And the kilograms of solvent, well, we have 125 grams of water, which is the solvent. So I just divide that by 1,000. Oops. So I have 0.125. So when I take this ratio of 0.05 divided by 0.125, I get moles per kilo, which is essentially equal to something called molal. All right. So when you talk about molarity, you say it's like 0.5 molar. All right. If you were to say it in molality, you would say it's like 0.5 molal. All right. So when you compute this, we get 0.4 molal. All right. Or you could just say 0.4 molal with the lowercase m, not the uppercase m. So it can be a little tricky. That's why I prefer to actually write out molal when I'm doing calculations that involve it, so I don't get tripped up between molarity and molality. All right. Okay, so now that we've defined those units of concentration, what I want to move on to next are our 4 colligative properties that we're going to discuss. All right, the first one is called vapor pressure lowering. All right, so I'm going to go ahead and give you a definition that works quite well for this. All right, so it's a rigorous verbal definition. So it says the addition of a non-volatile. All right, before we go any further, when I say non-volatile, this means something that will not evaporate or evaporate on its own without excessive amount of energy. All right, so something like sucrose, which is just table sugar, would be something that I consider non-volatile, right? I spill sugar out on the table. Unless the ants come and get it, it's going to be there the next day. Whereas something like rubbing alcohol, which is isopropanol, that is volatile. I put that on the table in a few hours, that will have evaporated away. So non-volatile substances is what we're talking about here to work for vapor pressure lowering, okay? So back to the definition. The addition of a non-volatile solute to a pure solvent will result in a solution with a lower vapor pressure. All right. So essentially what we're doing is, if we have a container with pure water, pure water is going to exert a vapor pressure, right? Because what's happening here is all the little water particles at the surface are spontaneously escaping, all right, thus creating a vapor pressure, all right? So what we'll go ahead and do is define that pressure. We'll call it PA, and we'll put a little star here. All right, and the star means we're talking about a pure solvent. Some textbooks you'll see it given PA naught, right, with the little naught symbol. That also indicates that we're dealing with the pure solvent. All right, so what I can do now is add solute. And the trick here is that solute has to be non-volatile, all right? So something like glucose or sucrose is a classic example, all right? So when I add the solute, now the water particles have to share surface area with the solute particles, all right? And since the solute particles are non-volatile, they're not going to contribute to the vapor pressure. So what you can kind of see from this cartoon is that there are now fewer water particles, the blue guys, that are trying to escape into the vapor pressure, or sorry, the vapor phase. And since there are fewer of them, we expect our pressure to go down. So the solution is going to have a vapor pressure that we call PA. All right, so this is the partial pressure of A, or solution A, pardon me. So we have pure water and now a solution. And by definition, PA naught is going to be a greater number than PA. All right, and this can actually be defined by a mathematical equation called Raoult's law. And Raoult's law says that PA is going to be equal to the mole fraction of A times P naught A. This is a pretty clever little law, because if you have pure water, then chi A is equal to the mole of water divided by the mole of water. And if there's nothing else, well, the moles of water divided by the moles of water is equal to 1. Thus, PA will equal PA naught, right? That's not a surprise, all right? But as soon as we start adding in a solute, what happens to our chi A, all right? So let's back up a little bit. I'm going to erase this. This is no longer pure water. You've put something in it, a non-volatile solute. So let's say we've got mole solute. Now what happens to our chi A? Chi A will now be less than 1. All right? So you're multiplying your pure solvent pressure by a number less than 1. You're now going to have a partial pressure of A that is going to be lower than the original solvent partial pressure. All right, so it's a clever little law, and you can use it to calculate the actual new vapor pressure of the solution. And I want to work through that example. So let's calculate the vapor pressure of a solution containing 92.1 grams of glycerin, and it has a formula weight equal to 92.1. Very convenient. And glycerin is a non-volatile solute. All right, it is a liquid, but it is non-volatile. All right. And 184.4 grams of ethanol. All right. And based on the mass here, we are dealing with more ethanol. All right, and that will be our solvent. .07 gram per mole is its formula weight. At this temperature, ethanol has a P naught equal to 0.178 atmosphere. Right, so that is the vapor pressure of the pure solvent, 0.178 atmospheres. All right, so now what we need to do is calculate this new vapor pressure, since we've added a non-volatile solute. And knowing that the vapor pressure is going to be lowered, we should be calculating a P that is less than 0.178. So let's go ahead and use Raoult's law to calculate that. So PA is equal to chi A times P naught A. All right. So we know what P naught A is. That's the pure solvent's vapor pressure. But now what we need to do is calculate chi A. And which substance is A? Is it the glycerin or is it the ethanol? All right. So A is defined as the solvent. All right. So whatever the solvent is, that's what A is, and that's what we need to do. All right. So chi A, that's the solvent, right? So the solvent is ethanol. So we need to know what the mole of ethanol is, and we divide it by the mole of ethanol plus the moles of what else is in there, and it's only glycerin. All right, so looking back at our problem, we do not have the moles per se. We're only given the masses. All right, so we're going to have to convert the masses to moles, and then we can calculate chi A. All right, so the mole of ethanol is equal to, let's see, 184.4 gram. Pardon me. That's the mass we've got, gram. And now we need the formula weight of ethanol, and it's 46.07 grams per 1 mole. So I do that math, and I take 184.4 and divide it by 46.07, and I get a value of 4. All right, so now I need the mole glycerin. All right, and I'm given 92.1 grams of glycerin, and its formula weight is 92.1 gram per 1 mole. See my grams cancel, and I'm left with moles. Of course, 92.1 divided by 92.1 is 1. All right, so I've got some nice pretty integers there. We got 4 and 1. All right, so chi A, again, is the moles of ethanol, which in this case was 4. All right, and we have 4 moles of ethanol, and we got 1 mole of glycerin. All right, so this is 4 over 5, which turns out to be 0.8. All right, so now I can calculate my new vapor pressure by saying PA is equal to 0.8 times 0.178 atmosphere. And when I multiply those two numbers together, I get 0.142 atmospheres. All right, so that is vapor pressure lowering. All right. The next colligative property I want to look at is actually just a consequence of vapor pressure lowering. It's boiling point elevation. All right, so let's think about this. If you decrease vapor pressure, all right, you will increase boiling point. Now, why is that? All right, let's go back to a little cartoon and our definitions. When we have PVAP, this guy, and then we have pressure of the atmosphere, all right, and they're kind of in this tug of war. When they are equal, you by definition are boiling. All right? When PVAP is less than the atmospheric pressure, you are not boiling. All right? So, if you all of a sudden lower the, let's say you're boiling right here, and then you start throwing in a solute, all right, a non-volatile solute. What happens to your vapor pressure? Well, the atmospheric pressure is not going to change, all right, because you throw salt into water, let's say. What's going to happen is your vapor pressure goes lower, as we saw with Raoult's law, all right? So if your vapor pressure gets lowered, then all of a sudden you're in a situation where your vapor pressure is lower than your atmospheric pressure and you're not boiling anymore. All right, so this is the kind of how do you cook spaghetti faster question, right? One way you could cook it faster is by salting your water. All right, the reason it cooks faster when you salt your water is because you put a non-volatile solute like salt into the water, thus lowering the vapor pressure. All right, and in order to get the water to boil, you have to increase its temperature up to there. All right, so you can increase that vapor pressure. Thus, you are doing what? Elevating the boiling point. All right, so a much easier way to explain why you salt your water when you want to cook spaghetti faster is because you can elevate the boiling point of water to a higher temperature, thus you can cook the spaghetti faster. All right, careful. Throwing salt in the water doesn't make your water boil faster. It just makes it boil at a higher temperature, thus you can cook faster. All right? Okay, let's get to the math here. Boiling point elevation through some mathematics can be derived as such. All right, so delta TB. So this is our change in boiling temperature. All right, so the B is for boiling, the T is temperature, and the delta means change. All right, and it's given by the following equation: IKF M. All right, and notice I'm using that dramatic lowercase m, so that is molal. All right, so let's kind of talk about the different parts of this equation. This is the change in boiling point. Temp. All right. I is something called the Vant. Oops. Messed up my little Dutch symbol. Van't Hoff factor. All right. And I'll explain what that is in a moment. KF is what we call the boiling point elevation constant. And that is intrinsic for, or it's specific for a solvent. All right, so water, chloroform, ethanol, they all have different boiling point elevation constants, and you can find those constants in your textbook at table 11.2. Along with those boiling point elevation constants, you'll also find the boiling point of the solvent at 1 atmosphere. So for water, we all know it's 100 degrees C, but the boiling point of ethanol, you know, table 11.2 will help you find that. Okay, and finally, M is molality. All right, so it's the molality of the solution. All right, so what is the Van't Hoff factor? All right, so for now, we're going to try to discuss this in terms of particles. All right, so if we take sodium chloride as a solid, right, and something like glucose as a solid, and these are both soluble in water, if we put them in water, sodium chloride is going to dissociate into sodium ion and chloride ion. All right. Glucose, however, is a discrete molecular compound, and you just break the crystal lattice that holds the glucose particles together, and you still just get glucose. All right. And we would say it is an aqueous solution now. So my question is, we have 1 mole here of these. How many moles of solute particles did we get over here? Well, it's 1 mole. All right. Sodium chloride is a little bit different though. 1 mole of sodium chloride is going to give us 1 mole of sodium ion and 1 mole of chloride ion. So sodium chloride is actually giving us a 2-for-1 deal, if you will. All right, we get 2 particles per 1 mole of sodium chloride, whereas glucose is a 1-for-1 deal. All right. So the Van't Hoff factor tries to make up for that, because remember, it's the number of solute particles. That's what drives colligative properties. All right. So if we were to look at the I for glucose, it's equal to 1. All right. And in fact, all molecular compounds, the Van't Hoff factor is equal to 1. So things like glucose, sucrose, glycerin, those are going to be I equal 1. All right. So molecular compounds, I equals 1. Now, ionic compounds, it's quite a bit different. All right. So if we looked at the I for NaCl, we would estimate that it's equal to 2. And what I mean by that is that for every 1 mole of NaCl, I estimate that I'm going to get 2 particles. All right. So these were estimated, and then later on, some mathematical equations could describe this behavior, but an experiment's always the best. So NaCl experimental is actually equal to 1.9. All right. So what this implies is that the ions are not completely dissociating away from each other when they dissolve into water. All right. So, a couple are getting what they call ion pairs. The Na plus and the Cl minus stay together when they dissolve. But don't fear, table 11.3 has all the Van't Hoff factors for ion compounds that we'll be using, and in a test or quiz situation, I would provide you with the Van't Hoff factors that are experimental. All right, I don't expect you to memorize all those values. Okay, enough with that. Let's take a look at an example. What would be the boiling point of a solution that contains 92.1 grams of molecular iodine, or I2, in 800 grams of chloroform. And the molecular formula of chloroform is CH11. All right. Okay, so this looks like we've got a solute and a solvent, and they're asking us about the boiling point. All right. So what we need to do is find a few constants that are going to be from table 11.2 in your textbook. All right. And what we can find there is we can find the boiling point. All right. So temperature that it boils of pure chloroform is equal to 61.26 degrees C. Now, if it were water, it'd be 100 degrees C, but we're dealing with chloroform rather than water here. All right. Another thing that we find in our table is the boiling point elevation constant of 3.63 degrees C per molal. All right, that's for chloroform. All right, we're ready to go. We can go ahead and calculate our delta TB equals IKF M. All right. And before we get it started, we need to figure out what our Van't Hoff factor is. Iodine is a molecular compound. It's an I bonded to an I. So it's going to be I equal to 1. All right. So iodine is molecular, so I will be equal to 1. All right. So I'm going to rewrite the equation here. So I equal 1. KF, we looked up in our table. That was equal to 3.63 degrees C per molal. And molality, okay, now what is that? So molality is a new unit of concentration that we introduced. So if going back in the notes, you'll see that it's the mole of solute divided by the kg of solvent. All right. So what information were we given? Well, I2 is our solute, and we had how much of it? 92.1 grams. Chloroform was our solvent, and we were given 800 grams. All right, and we can go ahead and convert that to 0.8 kg. All right, just divide it by 1,000, and I get 0.8 kg. So I'm good on my kilogram of solvent. However, I've got to convert my I2 solute mass into mole. All right, so what I'm going to need to do is find the mole of I2, right, because that's my solute. So it's 92.1 gram of I2, and we need the formula weight of I2. All right, so you can look that up online, or just get it off the periodic table by adding 2 molar masses of I on there. All right, but if you take I plus I, you will get a molar mass of 253.81 gram per 1 mole. All right, iodine is extremely heavy. All right, so our grams cancel. And when I do that, I find that I get 0.36 mole. All right. So we've got 0.36 moles. So now I've got everything I need to put this guy together. All right, so I'm going to start on a new page. Let me go back and make sure. Yeah, for some reason I make this mistake a lot, and I apologize. Kf is the freezing point depression constant that we're going to get into next. It's just a typo for me. It should be Kb, not Kf. Sorry if that led to any confusion, but Kb, all right? And that number is correct from the table, all right? So we know delta Tb is going to be equal to 1 from our Van Hoff factor. Kb for our chloroform is 3.63 degrees C per molal. And our molality in this case is 0.36 mole of I2 divided by 0.8 kg of chloroform. All right. So I will simplify that last number by just dividing 0.36 divided by 0.8, and I get 0.45 molal. So my molals cancel. So now it's just straight multiplication. 1 times 3.63 times 0.45, and I get 1.63 degrees C. Now, careful. This is equal to delta Tb, which means it's the change. My boiling point is not 1.63 degrees C, all right? I need to add 1.63 degrees C to my original boiling point. Why do I add? Because this is boiling point elevation, all right? So my new Tb is equal to 1.63 degrees C plus the original boiling point, which I can get from the table, was 61.26 degrees C. So adding those two numbers together, I get 62.9 degrees C. All right. The most common mistake I see in these problems is people will forget to add their boiling point elevation to the original boiling point temperature. So be sure to do that. All right. Okay. Finally, of the temperature-dependent colligative properties, we're going to look at freezing point depression. depression. All right, so what we're doing here is we're just going in the opposite direction. All right, so when we add a solute to a solvent, we actually lower the freezing point of that pure liquid. All right, so addition of a non-volatile solute lowers the freezing point of a pure liquid. And this is precisely how antifreeze works. All right. Antifreeze is an additive you put into your water in a radiator in your car. And what this does is ethylene glycol is a non-volatile solute. So what it ends up doing is it raises the boiling point of your water, which is good because your car is operating at very high temperatures, but it also prevents freezing of that coolant. All right, so they call it antifreeze. All right, and it lowers the freezing point of water, so it has to be much, much colder for water to freeze. All right, also this is how de-icers work. All right, so things like you put out on the roads or your walkway to melt ice. De-icers, what they do is they lower the freezing point of water. That way it takes a much colder day for the water to turn into ice. All right, so when they salt the roads or salt driveways, that's what they're doing here with these compounds. All right, so fortunately, table 11.2 is going to come in handy again, because not only does it have your boiling point elevation constant and your boiling points of pure solvents, you're going to find the freezing points of pure liquids there, as well as a necessary constant called the freezing point depression constant. So we have IKFM, so this formula looks almost identical, right, to the boiling point elevation. We have a change in freezing point. We have the Van't Hoff factor again. We have the freezing point depression constant, so it's Kf rather than Kb, and we have molality again. All right, so the exercise here is almost identical, say for one step. All right, it's the calculation at the end. So why don't we go ahead and say, what is the freezing point of a solution of, that is 0.33 molal glucose in water. All right. So glucose is a molecular compound again. All right. So our I is going to be equal to 1 since we're dealing with glucose. All right. Kf, that's the freezing point depression constant, and our solvent is water, so we need to look that up. All right. And from table 11.2, it's 1.8 degrees C per molal. All right, and the molality, that is already given to us, so that's nice. It's 0.33 molal. So now it's just plug everything in. All right, so my delta TF is going to be 1 times 1.86 degrees C per molal times 0.33 molal. Molals cancel. I'm left with degrees C. And my my change in freezing point is 0.614 degrees C. Now again, be careful. That's not my freezing point. My new freezing point, all right, is going to be that number subtracted from the original freezing point. All right. Why is it subtracted? It's because it's freezing point depression. So water has a freezing point of 0 degrees C, and I'm going to depress it 0.614 degrees C. So 0 minus 0.614 is negative 6.14 degrees C. All right, so that is my new freezing point for water. All right, finally, we're going to get into osmotic pressure. All right, and before we talk about osmotic pressure, let's go ahead and define osmosis. And osmosis could most easily be defined by a picture or a cartoon, if you will. So we're going to take a large container here, and we're going to fill it with water, and we're going to put a partition in there. And then we're going to put a pressure sensor in red. All right. And this partition here is something called a semi-permeable membrane. All right. That means some things can get through it. All right. So semi means kinda, and then permeable means get through it. All right. So you can kind of get through it. And how do you kind of get through it? Well, if we take water, these little blue dots, all right, and then we take something like sodium chloride. I don't want to use red. Let's do green. Okay, sodium chloride or some solute, right, cannot get through the permeable membrane. All right, and then of course we have water on this side as well. And the water can go back and forth, right, between the semi-permeable membrane. But we're going to have a net flow of the water trying to dilute the solute particles, all right? So the net flow, water will flow to minimize solute concentration. And remember, the solute are the green particles, all right? So what's going to happen is we're going to have a net flow going in this direction. So what do you expect the levels on each side of the container to do? Well, what's going to happen is the level is going to rise on this side because we have a net flow in that direction, and it's going to fall on this side. And if we had a pressure sensor built in, we could measure this pressure that is being pushed up here, all right? So we have a pressure that can be pushed right there, all right? And that pressure is called the osmotic pressure, all right? So osmotic pressure is defined as pi, all right? So capital pi, the Greek letter for P, is osmotic pressure, and it's given by the formula I, so there's our Van Hoff factor again, M, capital M this time. So this is molarity, RT. So pi equals IMRT. So I is our old Van Hoff factor that we've seen. M is now molarity. We've seen this guy before. This is mole solute per liter solution. Okay. T is absolute temperature. So this is the Kelvin scale. And R, I'll write it up here, is our old friend the gas constant. And this time we need the 0.08206, and the units on it are liter atmosphere per mole K. All right? So that's our gas constant, and it's just simply going to be plugging these numbers in. So I could ask, what is the osmotic pressure? of a solution that is 0.750 liter and contains 5 grams methanol, which is a molecular compound, in water at 37 degrees C. Okay, so osmotic pressure, we know our equation, pi equals I mRT. So since methanol is an molecular solute, I is going to be equal to 1. All right, M is our molarity. So that's going to be mole of solute per liter solution. That's going to require some calculations. R is our gas constant. All right. And T in this case is going to be 37 degrees C plus 273. All right, to give our Kelvin, which in this case is going to be 310 Kelvin. All right. So the only thing we really need to do is go calculate our molarity. All right. So we've got 5 grams methanol. In order to get to the moles of methanol, I need to multiply by its formula weight. So the formula weight of methanol is 32.04 grams per 1 mole. Now you can either look that up or calculate it from its formula. So the grams are going to cancel, and the mole of methanol I get is 0.156 mole. So now we can put everything together. Pi equals 1 for our Van Hoff factor. Our molarity we just calculated is, we calculated the moles. So it's 1.56 mole of methanol per liter of solution. Okay, there's my mole per liter. And then, let's see, IMR 0.08206, liter, atmosphere, mole, K. And finally T, which we said is 310 K. So we can simplify this by doing that ratio. So 0.156 divided by 0.750, it gives me 0.21 molar, or we can say mole per liter if you wish, times 0.08206 liter, atmosphere, mole, K, times 310 K. So our K's cancel, liters cancel, mole cancel, and we're left with atmospheres. Okay, so atmospheres are our unit of pressure. So let's see, I take 0.21 times 0.08206 times 310, and I get a pressure of 5.3 atmosphere. All right, so pretty straightforward, just some mass to mole calculations in there. So one place you've probably seen osmotic pressure is if you ever have an IV put in, they have these what are called isotonic solutions. They have usually some kind of potassium chloride solution in them. And the reason why, if you put an IV into, to up your fluids, it needs to be what we call isotonic, all right? Because if you have a cell, and then you have a solution, which would be your serum, all right? And if the concentration here was too high, right, what's going to happen from an osmotic standpoint? Well, a cell is a wonderful little semi-permeable membrane, all right? It lets water in and out quite well, all right? So in this case, this would be something called hypertonic. So your solution has too much what we call electrolytes or ions. So if there's too many electrolytes out there, all right, so let's say you eat too much salt, for example, or you take an IV with way too much salt in it, what's going to happen is the H2O inside the cell is going to go out of the semipermeable membrane via osmosis, and it's going to cause the cell to shrivel, all right? It loses its water, okay? Another scenario is where you have the cell, okay, with water in it, and then the solution here is too low in electrolytes, too few electrolytes. This scenario would be called hypotonic. So now what's going to happen is you have a higher concentration of solute inside the cell. Water is going to net flow through that semipermeable membrane into the cell, and you're going to put too much water into the cell, causing them to burst, all right? So this would be a bad scenario as well. So what you need is a solution that's not too high or not too low in electrolytes when you're giving an IV. You need it to not be hypotonic, nor do you want it to be hypertonic. You want it to be isotonic, right? So there's been a lot of work and studies about what an isotonic solution is for an IV, and that's just one place you would see osmotic pressure being adhered to. All right, well, that does it for this video. Thank you very much, and everyone have a nice weekend. We'll be back with more videos next week.